Good morning. My name is Patrick Love. As you probably know, if you've watched the introduction to this course called Climate Science: A Discussion for Everyone, the sessions that I'm gonna start recording today are about how the climate works, what the basic ideas behind how the climate works. So this is kind of a background for the rest of the course, so that we have some common language and understanding that we will be drawing upon when we look at the relevant questions of why the climate is the climate warming, or how is it warming, and so on. So we'll get right at it. I'm going to share my screen so that you can see the slides, because they're a lot more interesting to look at than I am, especially in these days where we're cooped up in the house because of the virus. Sooner or later here, I'm going to have to get a haircut, or I'm going to have to get a ponytail, one or the other. At any rate, so our discussion is going to be how the climate works. And there's basically going to be 3 lectures on how the climate works. We're going to talk about basic ideas. We're not going to get into too much detail, but the first section of this is kind of an introduction, and then something about radiation balance and how it affects the temperature and climate of the Earth. So we'll dive right into this. So it's sometimes confusing to think about what is the climate and what is the weather and how are they related and so on. So I thought what we would do is we'd start out with some questions that are clearly climate questions. What's the average temperature in December in Tallahassee, and why is it different than the average temperature in Rochester in December? You can see that Tallahassee's a little warmer, 56 degrees. In Rochester, the average temperature is 31 degrees, and obviously they're about 13 degrees different in latitude. Unfortunate degrees and degrees, slightly different degrees, but obviously Rochester, New York is a ways north. Here's a climate question. Columbus sailed to the Americas on easterly winds. You probably know them as the trade winds. When I say easterly, that means they come from the east. If you live in New York, you know that the winds come predominantly from the west, southwest. And you might ask, why are those things both true? So in New York, we have predominantly westerlies, but when you get down towards the tropics, they're predominantly easterlies. And we can understand that in terms of atmospheric circulation that's driven by the climate. Hurricanes form near the equator, head west and north. They spin into the northern hemisphere, and eventually they go off into the Atlantic. And we can explain that. And then another important climate question is, why is the climate of Los Angeles, California, different than Dallas, even though they're at roughly the same latitude? So while the first question gets at the latitude effect, the last question gets at effect that has to do with ocean and atmospheric circulation. So these are climate questions. You notice how different they are than weather questions, like, is it going to snow tomorrow in Dallas? What's the temperature going to be this week in Rochester, New York, right? Those are more weather questions. So we're going to try and answer these questions as we go through the course. And you'll find that the ability to answer these questions will come from understanding some basic ideas about how the climate works. So let's talk about big factors we need to know and how the climate works. So the first thing is, we know that basically radiation comes from the sun, it heats the Earth up, and the Earth radiates energy back into space. We're going to spend a lot of time in this beginning lecture about how that all works. We're also pretty well aware that the Earth is almost a sphere. It's a little heavy around the middle, like most middle-age objects, but that's from the spin. But basically, the Earth is a sphere. We know it rotates, and the fact that the Earth is a sphere is going to affect how radiation is distributed on the sphere. The Earth spins, and that spin, together with the unequal radiation as it hits the Earth, creates a complex flow of energy, basically tries to move energy from the equator to the poles. And that energy is moved both in the atmosphere and in the oceans. Also, the land, it cools off and heats up faster than the oceans. That's largely because the heat capacity of the oceans are so high. It takes less energy to heat the land up by a degree than water, because solid particles on the land can only vibrate, while there are more degrees of freedom for vibration and translation moving around in a liquid. Also, the hydrogen bonds in water take energy to break apart, and that then allows the molecules to move around more freely, but that amount of energy is absorbed. In doing that, it takes more energy to do that. And then, of course, when the water cools, they go back together and release energy. So basically, it takes more energy to heat water up. The oceans and the continents exchange energy with the atmosphere that's right above them. So you have air above the ocean and the continent, and they obviously come to some equilibrium where they're in contact. And that creates these things called air masses. So you get a moist, warm, marine tropical air mass that has humidity in it. It has a certain amount of absolute humidity, and it has a higher temperature, and it can move around, whereas a continental air mass might be a different temperature and drier humidity. Air masses come together at fronts, and when they come together, they create two different kinds of things. They create what are called extratropical, meaning outside the tropics, cyclonic weather systems. Cyclonic refers to cyclones, that is, rotating systems. And they also, when they collide, cause large parcels of air to ascend into the atmosphere, causing clouds and precipitation. And the last thing we know about the climate is the Earth is tilted, and it leads to different seasons. Obviously, the north and southern hemispheres are out of phase, but we know that those seasons happen. So what we're going to do now, in the next bit of this lecture, we're just going to spend some time talking about radiation balance and warming. What we know is energy moves from the sun to the Earth. And let's go to this next slide. The way energy is transferred is through waves. Now, you know of waves, material waves, like if you drop a pebble into the water, shown in the upper left of the slide, you get waves emerging out in a circular pattern. If you looked at any particular part of the water, it would go up and down, but it wouldn't go out. What's going out is the energy that was transferred from the droplet, from the thing that incidentally hit the water, to the water itself. There are sound waves. The one on the picture on the right up part of the screen is a sound wave. Pay attention to the gray mottled surface. That's actually the sound wave. It's a density wave. It actually goes through the air. When you hear me talk, there's a density wave that goes through the air. In other words, it gets more dense, then less dense, then more dense, then less dense. And that runs into your eardrum and causes it to vibrate. But the waves that travel from the sun are actually called electromagnetic waves. They are an electric field and a magnetic field that are perpendicular to each other. They have a wavelength, which means the distance between the peaks or the distance between the valleys. And if you look at the lower left, you'll see a spectrum. And what I mean by a spectrum is the energy you get at each wavelength. So right in the middle of the spectrum is a fancy colored red to blue spectrum that you're used to thinking about. That is visible light. It comes in at a certain frequency and wavelength. You may notice the scale on the top is in meters. 10 to the minus 6 is basically sometimes called a micron. In other words, 1 micron is 10 to the minus 6 meters. And visible light is right around a micron or less, right? You're familiar with a lot of these other names for pieces of the electromagnetic spectrum. So if we go to the left, we have infrared light or heat energy. That is a electromagnetic wave. It's a longer wavelength than visible light. And then microwaves, your microwave warming your food, and TV and radio waves, which are quite a bit longer. So radio waves have energy, have wavelengths around 10 meters. And if you go to the right, you get ultraviolet rays and X-rays. Now we're only going to use the center of the spectrum where the sun emits most of its energy. So if we go back to thinking about this idea of a spectrum, that means that, so if you look here, we have the Earth's spectrum and the sun spectrum. Again, the bottom scale, and this scale is in microns. The bottom scale shows you that the Earth spectrum is centered around 10 microns, whereas the sun spectrum is centered around 0.5 microns or something like that. What that means is we know that the sun spectrum is basically peaks in the visible light, whereas the Earth spectrum, the energy that the Earth emits, is peaked more in the infrared. So basically what comes off the surface of the Earth is a lot of heat energy, if we want to call it heat energy. You, for example, as a human being, have an average temperature of, let's say, if you're healthy, 98.6 or something like that, degrees Fahrenheit. The Earth's average temperature is about 59 degrees Fahrenheit, whereas the sun's average temperature is about 5,000 to 6,000 degrees Kelvin, or about 10,000 degrees Fahrenheit. So it's much hotter than you or the Earth are. And as a result of being much hotter, it puts out more energy, the peak is higher, and it shifts the peak towards shorter wavelengths. So the idea is that as you cool off, you move to the left on this scale, right? So if you look at your fireplace, for example, and let's say there's a fire in your fireplace, you look at your fireplace, you can feel the infrared energy coming off it, but you can also see visible light, right? That's because the fireplace gets up to 1,000 degrees Fahrenheit or slightly more. The gases in the fireplace, when they burn, the wood in the fireplace burns more at 500 degrees Fahrenheit. And so basically you get a spectrum that overlaps a little bit for a fireplace. So hotter objects emit more energy than colder objects, and hotter objects emit at shorter wavelengths, so they shift to the right. Another important factor in looking at this curve is if you add up the energy at every wavelength under these spectra, you get the total energy emitted by either the sun or the Earth, which will become important for us later. And there is a very simple, there's a little bit of physics here, so some warning. There's a very simple relationship that basically says the total energy under one of these spectra for an object emitting at a temperature T is basically a constant called sigma times T to the 4th power. So if you add, for example, if you start with the sun spectrum just to the right of 10 microns and you start adding up at each wavelength what's under the sun spectrum, you will find that that total adds up to something proportional to T to the 4th, right? And that's important for where we're going with the rest of our discussion. So you are a power plant. As I say, you have an energy. You're mostly seen, if we were to look at you, we see reflected light coming out off you. And so we see your image in reflected light, but you're actually emitting infrared energy. And if you've ever seen like an infrared pair of binoculars or infrared glasses you can wear, you see human beings as a glow. Because the infrared's longer wavelength, you don't see the detail you see. The reason you are a little power plant is you eat plants which have carbohydrates, basically carbon and hydrogen bound together, as shown in this picture. The center picture here is a glucose molecule. You process this glucose into ATP, which, if you remember the Krebs cycle from your biology class in high school, you use to make energy in every cell. And so basically you're burning carbohydrates just like a power plant to make energy, and you emit that energy off your body as infrared energy at 98.6 degrees. So let's go back though and go through, we're going to go through a little calculation. So we're going to go back and look at energy coming from the sun. It takes about 8 minutes from energy from the sun to traverse the 93 million miles to get to the Earth. It comes in electromagnetic form. It comes principally at wavelengths in the visible, although you saw before it is spread out. And what we know is that if we put a satellite out in space, it measures the total energy coming at us at about 1,364 watts per square meter. That is, and let's talk about what a watt is. So you're familiar with light bulbs in your house, and you may know that you may have changed bulbs. A 60-watt kind of light bulb is a normal bulb for a lamp. The actual unit of energy is joules. We don't have to go into too much detail there, just to know that that is an energy measurement. A watt is basically energy per second. So when we say a satellite measures 1364 watts per square meter, imagine that you have a 1 square meter piece of paper, a flat plane. It would intercept 1,364 joules per second, that much energy per second, right? That corresponds to about 23 60-watt light bulbs. So this much energy is coming towards the Earth. Now, up in the upper corner, up in the center part, it has a fancy formula. It says pi times the radius of the Earth squared divided by 4 pi times the radius of the Earth squared is equal to 1 over 4. That's not a surprise, is it? The pi RE squared, but cancels out. But the question is, what the heck is the formula there for? Well, the formula there is to say what actually energy on average falls on a square meter on this spherical Earth when we measure in a flat plane out in space on a satellite. And the answer is basically 1/4. If you take the Earth's shadow divided by a flat plane of the Earth's shadow divided by the Earth's surface, you get 1/4. Another way to look at that is that the surface area of the Earth is 4 pi r squared, right? This RE, the radius of the Earth squared. And we're spreading the energy that's in that circle on the measured by the satellite over the whole surface area. So that's how you get that 1/4. Why is that important? Well, because we're going to talk about that in just a second. Now, I'm going to warn you that we're going to do a little bit of math and a little bit of physics here. So this won't last long. It won't be very painful. It has a very simple conclusion. You only have to remember the conclusion, but I'm always tempted to walk through these things with people. So basically what we're saying is the sun's intensity in space is 1364 watts per square meter. A watt is 1 joule per second. That means that what the Earth absorbs, or at least is what targeted at the Earth, is that L, which is 1364 divided by 4, right? What's actually absorbed by the Earth? Well, it turns out some of the Earth reflects the energy. In fact, certain kinds of clouds, the ice on the Earth, what's called the cryosphere, all the ice on the Earth is very bright and white. And of course, any object reflects some light, right? It turns out that the average reflectivity of the Earth, which is called the albedo, is about 30%. So what's actually absorbed by the Earth's surface is L divided by 4, which takes care of the geometry problem, and 1 minus what we're going to call alpha, right? So that's what's absorbed. Now, the Earth radiates energy, and I told you earlier, because of this basic formula for the total energy radiated by an object at all wavelengths that object radiates, we can say that the energy radiated by the Earth is a fancy epsilon times a constant called sigma times the fourth power of the temperature of that object that's radiating, in this case, the Earth, right? Now we're going to assume epsilon equals 1. You can forget about epsilon. It's not terribly important. And basically, we're making an assumption that all the wavelengths have similar opportunity to radiate. The constant, the sigma, is a famous constant. The numerical value is not important to you. I'll show you what to do with it. But it's basically a constant called the Stefan-Boltzmann constant, right? And we'll change the page. So one of the things that's a basic physics principle, that if an object receives energy, the energy it receives will eventually balance with the energy that it puts out. If, for example, that object were to receive more energy than it radiates away, then it would raise its temperature until it was equal, okay? Now, this is a very basic result from physics, so there's nothing surprising here. What this means is I can take the energy in, which on the previous page, whoops, went the wrong way, which on the previous page you may know as L by 4 times 1 minus alpha. I can equate it to sigma t to the fourth, where I've assumed epsilon is 1. And I can do a little bit of mathematics, not important, and I can calculate what the Earth's inner temperature would be if it were just a rock and it were in equilibrium, right? Now, we haven't assumed, this is assuming that the Earth has no atmosphere. Basically, we're sort of assuming that the Earth is just a solid object. It turns out that's not, that doesn't change the radiation balance. The Earth, whether it has an atmosphere or not, will reach a radiation balance. But we know something about gases. Gases behave slightly differently in the way they radiate energy, and we're going to get to that soon. But basically, assuming the Earth were just a rock, our temperature, given a current radiation intensity coming from the sun, would be effectively 0 degrees Fahrenheit, right? So this is called the bare Earth temperature. And we understand that that's a lot colder than what we actually experience. The actual average Earth temperature in 2018 was 59 degrees Fahrenheit, right? So this tells us that something else is going on. We know what else is going on, actually. It's the atmosphere. And we're going to walk through how the atmosphere affects this and changes the temperature of the Earth by the surface of the Earth by 60 degrees, right? What this tells us, though, is that it tells us that if the Earth is warming, then it must be true that there's more energy coming in than is leaving. So when we get to the section that asks, is the Earth warming, we will end up sort of using that fact to help us understand why it might be warming and whether it is or not. Okay. So the point is, without an atmosphere, we would actually be at 0 degrees Fahrenheit. Now, this has been known for a while, and it's called the greenhouse effect, and we're going to talk about that more as we get into this section. Okay. So now we leave the math behind. You can all breathe a sigh of relief. We're going to look at some data. So this is data measured at the top of the atmosphere and at the surface of the Earth. And basically what we're looking at here is the spectrum that I've spoken of, right? This is the incoming radiation spectrum. So the scale on the left should be read as an intensity of radiation. Along the bottom, you have the wavelength. That means that at each one of those wavelengths, you can follow the graph up to the intensity. Now, the smooth line on there is the calculation of what's called the black body temperature. In other words, spectrum, black body spectrum. That's actually a theory. That's a well-known theory of what objects radiate at each wavelength as a function of temperature, right? The yellow are actual measurements. So the spectrum, the black body spectrum, the smooth curve says the sun's photosphere, as we're putting in at 5,250 degrees centigrade. So we're basically saying that is the temperature of the sun's photosphere, which emits most of the energy that comes to the Earth. The yellow is the actual distribution as it reaches the Earth. So you notice there are slight differences in certain places. There's a little more energy in the visible than you might expect from that number. There's a little less further out at maybe 1,000 nanometers, and at the short wavelength end at 250 nanometers. The red curve is what actually makes it down to the surface of the Earth, right? So that is the radiation at sea level. What you'll notice is that the red curve is dropped down. In other words, sort of has two things going on with it. It's essentially shifted down, and that shift is principally because of the reflectivity of certain objects on the surface and in the air, the clouds and the cryosphere and various parts of the Earth's surface. For example, deserts reflect a lot of light. But then the other thing that's going on with that red spectrum is there are big chunks taken out of it. You'll see a chunk at 250 nanometers. I should mention one thing. The bottom scale is in nanometers. You may know that that is 1/1,000th. A nanometer is 1,000th of a micron. So 250 nanometers is basically 0.25 microns, right? So your favorite visible light is between 0.3 microns up to maybe 1 micron or 0.75 microns. For example, 750 nanometers or 0.75 microns is red light. And then obviously as you get down to 300 or so nanometers, you're down in the purple light. And then you go into the ultraviolet below that. So it turns out that certain molecules in the atmosphere, principally oxygen and water, a little bit of CO2, but the CO2 effect in transmission through the atmosphere from the sun is mostly down at the 2,000 nanometer or beyond 2 micron range, right? So you also see that the ozone, which is O3, right above the 250 nanometer range there, cuts off the spectrum. And we know this. You remember there was a whole concern about the ozone layer and it being disturbed because of chemicals we were putting in the air from some of our thermal fluids, typically the hydrofluorocarbons that we used in our air conditioners and stuff years ago, refrigerators. There's an important role there because we don't want that ozone, we don't want that ultraviolet light to reach the surface, right? It does a lot of damage both to organic and inorganic things. And so ozone is very important to us. And that ozone is mostly up in the stratosphere, but it is affecting the spectrum there. The other molecules are affecting the spectrum at the Earth's surface. So that is the energy that reaches the surface, and we could sum that up, and we would find out that if you add up the red spectrum, you get something like 160 watts per square meter that reaches the Earth's surface. So you remember we're spreading 1364. We divide that by 4, and then basically some of that's reflected, and then some of that is absorbed by some of these molecules coming through. But principally, in the peak energy range, the Earth's atmosphere is pretty transparent to visible light, where a lot of the energy is coming from. And it's a simplification to say that, of course, but it's pretty much true. The difference is not so much what gets absorbed in that region, but what gets reflected, right? And that's why the albedo is important to our temperature. All right. So now I have one beautiful picture of the sun's corona. Sun's corona, if you look at this picture, the photosphere is kind of the spherical version, the spherical shadow you can kind of see. It's very hot, as we said, it's over 5,000 degrees centigrade. But the corona are these flares that reach out from the surface of the photosphere. And that's where the ultraviolet light is coming from, because they're even hotter, right? So they generate some ultraviolet light in the part of the spectrum, the very high frequency part of the spectrum. Okay, now our atmosphere, let's just spend a little time saying what the atmosphere is composed of. Our atmosphere is in some ways, a very simple gas without a lot of other things mixed in. For example, if you just counted molecules of each type, so you just did it by number, nitrogen represents 78% of the atmosphere, oxygen another 20%, 21%, argon maybe 1.2 or 1.3%, and everything else is so small that we have to kind of count it in parts per million, right? So water vapor is still a decent amount, but it varies dramatically. So when water vapor is in a constant water cycle, from liquid on the surface, heated, goes into the atmosphere, comes back down. If you're in over a desert, you're close to zero, but wherever you are, you may have water vapor in the atmosphere depending on the temperature, and depending on the availability of water in the area. Now, the next biggest molecule after water vapor is carbon dioxide, and we measure that in parts per million. Remember, this is by number. So basically, for every million molecules of air, every million molecules of the top ones above, nitrogen, oxygen, argon, and so on, you get 411 molecules of carbon dioxide. Now, that is the average number in December of 2019. I'm going to show you in the future, in a future lecture, that that number has gone back and forth between about 180 ppm and 280 ppm over, say, 3 million years of past Earth's history. We are currently well above the upper experience of the Earth, and that's what people say when they say carbon dioxide has been driven up by the Industrial Revolution. Then there are other smaller quantities that get small pretty fast. You notice ozone is down at 0 to 12 ppm. It varies regionally, and so on. I'm not going to go into all the detail. The bottom line is you get down to some molecule like methane. It's in parts per billion, so it's not even on this graph. However, methane has a large thermal effect, which we're going to talk about later. So that's the atmosphere we live in. Here is, to give you a feeling of the Earth's albedo, this is a beautiful photograph of the Earth that shows how bright the Arctic sea ice is. That's the Arctic sea ice. You notice Greenland has ice covering it, although it's darker. It's a sort of grayer. It's a multi-year ice. It's been there longer. The Arctic has fresh snow on it in this photograph. And you can look at some of the albedo. So the albedo should be read as the percent reflectivity to visible light. So for example, asphalt is very absorptive. It doesn't reflect much, only 0.04%. 4%. 0.04 of the light incident gets reflected away. The ocean is quite absorbent. only 6% of the energy coming in is reflected away. And so you get down to forests. Forests absorb a lot of energy. Bare soil is 17% energy reflected, and on and on. You get down to fresh snow, you get up to 80% of the light that comes in is reflected. So that gives you a sense of where that albedo comes from. So when we say the Earth is 30% on average, we're averaging over a lot of surfaces, right? Now, this is the emission spectrum at the top of the atmosphere. So this is basically now from a satellite sitting in orbit, looking down at the Earth and measuring what the Earth is sending back out, right? And you can look at this. The dashed lines are that theoretical expression of what the energy should be for an object at that temperature, right? So basically what it's saying is, if you look at this, it appears that a lot of the Earth's radiation spectrum, ignoring the big divots in it, the big holes in it, is at around 290 degrees, 295 degrees Kelvin, which is about 60 degrees Fahrenheit, which is what we expect, right? The Earth is about 60 degrees Fahrenheit. That's a little warmer than it's been for a long time, but that's what it is today. And it roughly, in certain ranges, the spectrum seems to match that curve. However, in other ranges, in other regions of the spectrum, there are big holes. So you notice there's a big hole, and underneath the bottom of it, it's labeled as CO2. Basically, that energy has been taken out of the spectrum. Let me tell you how that works. Carbon dioxide, shown over to the right is a little cartoon. At the bottom of it, it says 14 microns. Basically, what it's saying is across the top, you'll notice on the scale on the top, the wavelength is in microns. So there is the CO2 line is around 14 or 15 microns, right? So if you look at CO2, it has a carbon atom in the middle and two oxygen atoms, kind of as wings, if you want to think of it that way. And it turns out the carbon atom can act like a slingshot. It can basically, if you hit this with just the right energy, just the right wavelength energy, basically around 14 or 15 microns, you hit that molecule, the carbon atom will vibrate back and forth. And it will do that for a while. It's called exciting the molecule. Basically, hit it with some energy, it excites the molecule. It does that for a time, then it relaxes and emits that energy again, and sends it in all directions. In other words, isotropically sends it. So the reason this chunk is taken out at 14 or 15 microns is because basically energy coming from the Earth's surface, infrared energy coming from the Earth's surface, which contains 14 micron energy. In other words, that wavelength is too long for visible light. It's in basically heat energy, what we call infrared. Starts out at the Earth's surface, starts going up through the atmosphere. It gets up in the atmosphere and it runs into a CO2 molecule. And it gets absorbed, the energy is used by the molecule to vibrate, and then it emits this energy again in all directions. Now it can emit it back down, or it can emit it up, or emit it at various angles. Gradually, it emits it up, and so the energy goes up through, keeps running into CO2 molecules, and keeps this process going from molecule to molecule. Until it gets up to wherever the heck it is, 220 degrees Kelvin, right? Because clearly at 220 degrees Kelvin, it escapes into space. So you might say, where is it 220 degrees Kelvin? You see the dashed line with 220, and you see that this spectrum, where the CO2 line is, or the CO2 divot is, if I'll call it that. That's not a technical term. A scientist would call that a spectral line. I'm calling it a divot. But at any rate, the 220 theoretical curve intercepts the bottom of that divot. That's saying that at 220 degrees, basically that's at about 8 or 9 kilometers or about 5 miles up in the Earth's atmosphere. Well, what's the temperature up there? Well, it turns out the temperature up there is 220 degrees Kelvin. So what we're saying is this CO2 line acts like a chimney as the energy goes up, and eventually it reaches the point in the atmosphere near the top of the troposphere where it radiates this energy into space and it escapes. But in having done so, it keeps putting energy in all directions, back down, sideways, and so on and so forth, so that the amount of energy that is, so basically it's taking a chunk out of the spectrum. You'll see that ozone takes a chunk out. You see the CH4 line out there, sort of around 1,300 centimeters or 8 microns, just past 8 microns, depending on which horizontal line you're looking at. And CH4 is methane, by the way. Sorry about that. O3 is ozone. And then, of course, your favorite, water. It turns out that there are a lot of lines in here, as you can see. And a lot of, so we could go in and blow this thing up and analyze every molecular line. And a lot of that, all those are well understood physics. The theory behind those lines, the theory behind absorption and emission of radiation by materials is called quantum mechanics. There's quantum mechanics explains a lot of other things too, but it does a brilliant job of explaining these things. And so we understand those, all that hash that's on those curves. The bottom line, though, is if you look at the spectrum at about 11 microns, in that range, what we know is that the atmosphere is very transparent to 11 microns. That is, there aren't molecules that absorb energy in that range. And so that's coming directly from the surface of the Earth. And that's what's following the 295 degree Kelvin line. Well, what's happened here is these molecules have taken energy out of the spectrum, re-radiated it back down at the Earth or in all other directions, and that caused the Earth's surface to warm up. It has to warm up in order to compensate for all those divots. Because, as we said, the Earth is trying to radiate away the energy that it's receiving from the sun. Otherwise, it will warm up. And it is, of course, we're going to talk later about it warming up. But this basic effect is called the greenhouse effect. A bit of an unfortunate name because it doesn't exactly act like a greenhouse, but it is called the greenhouse effect. It's been known since the effect of CO2 on, in the particular CO2 gas, the effect on thermal radiation has been known since 1753 or 59. The prediction of its effect on the Earth's temperature was done in 1896, I think, by a guy named Arrhenius. And so we've known these things. And basically, the greenhouse effect causes about a 60-degree change, 60-degree Fahrenheit change today in the average surface temperature of the Earth. Without these molecules absorbing energy, leaving the surface of the Earth would cool down to, it would be able to radiate its energy at something more like 0 degrees Fahrenheit. So we'd be a lot colder. At any rate, that is our first installment of understanding the climate. I am going to stop now. The second installment is coming in the next lecture. Thank you. Thanks for being here.